Hello and welcome to Slice of Physics. In this Slice of Physics I'm going to talk about Snell's law, which is a rule for understanding how light bends when it passes from one substance into another. This bending is called refraction. So let's take an example. Suppose there's some water. This might be a lake. And I'm going to draw these lines to show you where the water is. This is the water, and above it is the air. So water, air. Now let's suppose that a ray of light comes down and hits the water. Let me draw that as a straight line. Now the question is, does this ray of light, when it hits the water, does it go straight through like this? Or does it actually bend? It turns out that the light will bend when it hits the water. Now the next question is, does it bend in this direction? Does it bend up? Or does it bend down in this direction? So it turns out that the light bends down. So I'm going to draw the light bending down. And one interesting question is, how can we describe this bending? So when I say it bends down, then that's very descriptive of what happens when the light from the air hits the water. But let's think of another example. Let's suppose that there's a cup of water. Suppose there's a glass of water like this, and here's some water, and some light, a ray of light hits it like this. So how does the light bend? Does it bend down? Or what if the light is coming in this way? So now the light doesn't bend down, it actually bends sort of more up. So how do we describe the bending of this light? Well, the way we describe it is we invent the idea of the normal line. So the normal line is perpendicular to the surface. There's the normal. And what we care about is whether this ray of light bends closer to the normal, that is towards the normal, or does it bend away? So if the light bends like this, then it's bending toward the normal. Now we don't have to use this unclear language about bending up and bending down. So if another light ray were to come in here, like in this direction, then it would bend also toward the normal, like this. So you can see that one of these light rays is bending down and the other is bending up, but both of them are bending toward the normal. So from air, when a light ray bends from air to water, it bends toward the normal. And once it reaches the glass again, what happens when it bends its way out? Well, when it goes from the water to the air, it bends away from the normal. So there it is, bending away from the normal when it hits the other side of the water. Okay, so that tells us from water to air, it bends away from the normal. Okay, what about if there's some other substance, let's say glass, when it bends through a large piece of glass? All right. The general feature of these substances that characterizes them gives them the letter N, which is the index of refraction. And for air, we say that N equals 1. For water, N equals 1.33. And for glass, N equals 1.5. So the general rule is that if the initial index of refraction is greater than the final index of refraction, then the refraction bends toward the normal line. If the second index of refraction is greater than the first, then the light will bend away from the normal. So for example, if I were to make a lens, this is a lens of glass, and some light were to come in, say some light comes straight in like this, then if I draw the normal, now the normal is perpendicular to the lens, so it looks like the normal will look like this. So I'm drawing it perpendicular to, so here's a line tangent to the lens, and the perpendicular line is perpendicular to that lens. So to that tangent. So if it were to go straight through, the light would go straight through, it would look like this. But we know that it's actually going to bend toward the normal because the initial index of refraction is 1, and the second index of refraction is 1.5. So the second index of refraction is bigger, so that means that the light will bend in like this. Now when it gets to this point, the tangent line looks like this, and the normal looks like this. That's perpendicular to the tangent line, and we know that the ray of light will bend away from the normal because it's going from a high index of refraction to a lower index of refraction. So that means that if it were going straight through, it would look like this, but actually it's going to bend away from the normal, so it will look like this. So you can see that as a result of passing through this lens, the light bends twice. It bends down twice in a row, but the first time it bends, it's bending toward the normal, and the second time it bends, it's bending away from the normal. And that's because the two normals point in two different directions, because the lens is curved. So on one side, the normal points down and to the right, and in the second case, it points up and to the right. So what is this N, by the way, the index of refraction? The index of refraction tells you how light bends, and it also tells you the speed of the light. So the speed of light is c, it's given the letter c, equals 3 times 10 to the 8th meters per second. That's 300 million meters per second. But that's the speed of light when it's going through space, through outer space, or vacuum with nothing in it. When there is something there, the speed of light is slower. So the speed of light in air is basically the same as the fast speed of light. But the speed of light in glass is only 2 times 10 to the 8th meters per second. And we say that it's equal to C, so C air is equal to 3 times 10 to the 8th meters per second. This is the speed of light in vacuum. So the speed of light in glass is speed of light in air divided by 1.5. This is the n. So speed of light in a certain medium, in some transparent medium, is equal to the speed of light in air divided by the n of the medium. That means that the bigger the n, the slower the light goes in that material. So light goes slower in water than it does in air, and it goes slower in glass than it goes in water. Okay, so one more thing I want to discuss is Snell's law. So Snell's law is written that n1 sine of theta 1 equals n2 sine of theta 2. So this rule is for when there's some boundary and the light is going to hit the boundary, and then it's going to refract in, let's say, or it might refract, so it might refract toward the normal, it might refract away from the normal. In this picture I have it refracting toward the normal. And then we'll call theta, this is going to be theta. So this is theta 1, and this angle is theta 2. And this medium has an index of refraction n1, and this medium has n2. Then this equation just relates the two angles and the two indexes of refraction. So one thing you can see is that if these angles were the same, then the indices of refraction would have to be the same. So whenever the indices of refraction are the same, then these angles are the same, and if these angles were the same, then the light ray would go straight through if the indices of refraction were equal. But you can also see that in this case, when in this picture n2 is bigger and theta 2 is smaller. So this equation tells you that if these, for a given value of n1 and theta 1, the bigger the index of refraction number 2 is, the smaller the theta 2 is going to be. So in this slice of physics, we've learned about Snell's law, which says that n1 sine theta 1 equals n2 sine theta 2. And we've also learned about how qualitatively that that if n1 is greater than n2, then the light will bend away from the normal. And if n2 is greater than n1, then the light bends toward the normal. And we learned how to draw the light bending in a lens. We drew a glass lens that bent the light or refracted the light. Okay?